I'm going to talk about learning and integrated information. This is work that I've done together with my PhD advisor, Nihat Ayn. But before I'm going to get to learning, I'm first going to talk about integrated information and morphological computation. There I'll first give you a first intuition into these different two concepts, then show you a small toy example where we did experiments that led to results, which lead to an open question or a problem that they will then address by talking about integrated information and learning. There again, I will give you an intuition, then we use the same experiment as before to generate some results that I will then explain. For some of you, the first part of the talk, integrated information and morphological computation, might seem familiar because last year in the online conference I presented this part. So let's start. I'm going to start with an embodied agent that's situated in an environment. So an embodied agent has some kind of sensors. Here these are the eyes of the agent that receive information from the environment. This information is then sent to the brain, the controller of the agent. There it's processed somehow. Then the signals are sent to the actuators, in this case the hands, that then can move and influence the environment, the balloon here, and thereby influences what the agent sees next. So these are the different information flows in our system that I just described, and now we're going to look more closely on two of these information flows. The first one is the one in the brain, and there we're going to measure it by something that I call integrated information. So most of you know the integrated information theory developed mainly by Giulio Tononi and co-workers. This is a theory that started out as a measure for brain complexity and developed rapidly in recent years through various stages of development to a broad theory of consciousness. Well, because of these different stages of development, there exist various measures for integrated information theory, depending on which iteration you refer to or which application you're in. The measure we are going to use here is an information geometric measure that follows the intuition that Tononi expresses in this statement here, that in short, integrated information captures the information generated by causal interactions in the whole over and above the information generated by the parts. So the measure that I'm going to use is one that we published here in the paper Complexity as Causal Information Integration, and I will define it in more detail later.
Excuse me, can you use the mic?
Okay, yeah. Of course. I don't know if that's turned on.
You have to turn it on.
Little button at the bottom.
Ah, now?
Wait for 3 seconds.
Okay, now? Okay, great. So this is the integrated information on the inside of the agent, and now we're going to look at the interaction of the agent's body with the environment, and there we're going to calculate morphological computation. Morphological computation is defined as the reduction of computational cost for the controller resulting from the interaction between the body and the environment. So an example for this is the passive dynamic walker. This is just a mechanical robot that can walk down the slope on its own without any control involved. Then, of course, in nature, we have many different examples for that. For example, the geckos that have feet with a morphology that can allow these animals to stick to very smooth surfaces. And, of course, the field of soft robotics, where the soft tissue of the robot's body allow the scientists to use controllers that are much less complex to, for the robots to, for example, grasp fragile objects. So now we have these two sides, integrated information on the inside, morphological computation on the outside. And the hypothesis that we had was that the more the agent can rely on the interaction of its body with the environment to solve a task, so the more morphological computation there is, the less integrated information in the brain is required. This was the hypothesis that we had, and now we're going to look at the small experiment that we did. So we have small artificial or simulated agents in an environment. Our agent consists only of a round blue body with a small blue tail. And in front of the agent, they have two binary sensors. These are the black lines here. They turn green when they touch a wall of this racetrack they are in here. And they are black if they don't detect the wall. And they are moving in the following way. So this is how the agents walk. They detect a wall, touch a wall, the body turns red, and then they are stuck. They are stuck as long as both sensors or one sensor still detects a wall. So here again, the agent touches a wall, the only thing it can do is turn, and now it can move away. Okay, the goal of the agents is to not be stuck at a wall, of course. So, now, what we also can do is to vary the reach of the sensors. So on the right here, you can see that the sensors can vary from small to long, and by that we can directly influence how much of the environment these agents can perceive. So we can influence how well they can interact in their environment, and thereby how much morphological computation they can use. Okay, the agents are actually modeled as multidimensional, discrete, time homogeneous macroprocessors that factor according to this graph here on the right. So we have the sensors on top, ST, that sends information to the sensors in the next point in time. This information is the one that goes through the world and directly sends information to the actuators, AT. Then the sensors also send information to the controller, C, which sends information to the actuator and to the controller next point in time. Additionally, we have an S prime here. This is the internal prediction of the next point in time. We will talk about this in more detail later. And here in the middle, we have the transition probability of time step t minus 1 to time step t. Here we see that these are then the conditional distributions of how the agent moves. And then we can adapt these conditional distributions, optimize them for this goal to stay away from the walls. The sensors, so ST consists of actually 3 binary nodes. So sensor 1, sensor 2, and a binary node binary variable that tells you whether the agent is stuck at the moment or not. Okay, we are for optimizing the policies, we're actually using something called the EM algorithm. This is a well-known information geometric algorithm, but I'm not going to go into detail for that here. Okay, so now we have the transition probabilities, and then we can actually calculate the matter. So when we, for example, want to measure how important the information flow from ST to ST plus 1 is, so the information that flows through the environment, then what we do is we define a set of probability distribution that we call the split system, in which this interaction does not exist. So where ST has no influence on ST plus 1. And then we minimize the KL divergence between the split system and our actual full distribution, so the one that actually happens. That then measures the strength of this connection, because if this measure is 0, then there is no difference whether this error there or not. So we have then no influence from st to st plus 1. In this way, we're going to define the different measures. And now we get back to integrated information and morphological computation. So what we did is to take 500 different initial distributions, so 500 different agents, and let them run for 20,000 steps. And it is important to know that if these agents would just move randomly, then after 20,000 steps they have a success rate of roughly 8%. The success rate is something that we sampled. That just means that roughly 8% of the time the agents were not stuck. And so we call agents successful if their success rate is roughly double as that, so above 16%. Now we can get to the results. Here on the left we see how we calculate the measures for morphological computation and integrated information. So morphological computation is, to reiterate, the interaction of the agent with its environment. So it's the information that flows through the environment. So there we have the connection above here that we measure. And for integrated information, we measure how much information is integrated across different nodes, across different points in time. So here we see this, the errors that are dashed are the ones that are measured. So we see that this is the information from CT2 to CT plus 1, 1, and from CT1 to CT plus 1, 2. And now we get to the results. And here we see with the length, increasing the length of the sensors allows the agents to use more morphological computation. And of course, if the sensors reach a certain length, then they almost all the time detect the wall, and therefore the morphological computation doesn't increase anymore. And on the bottom we have the integrated information, and we see that our hypothesis was right. So we have this antagonistic relationship that with the length of the sensors, the integrated information decreases. Apart from the last steps where the task gets harder again because the length of the sensors are simply too long. Okay, now what's the problem here? The problem is that this leads to the conclusion that embodied intelligence is correlated with reduced conscious experience. I think I have 10 minutes left, right? Okay, yeah, same. Yeah, 5 I think. Okay. So we could imagine that we could build a robot that's so adapted to the environment that we just don't need a controller. We don't need integrated information and thereby no consciousness. So there are, of course, different answers to this problem. One very obvious would be that our task was just way too simple. These agents can do without a controller. They just detect a wall and steer away, that's fine. But we can actually give also in this small example a different answer by looking at integrated information and learning. So our hypothesis now is learning to perform a task requires integrated information. So why are we thinking about learning? So consider a child that tries to learn how to ride a bike. So everything that the child learned before, walking, speaking, drawing, is easier when you do it slowly. So you reduce the pace, you do it more, you can do it easily. But riding a bike is different, because if you go fast, then the bike actually stabilizes itself. So the world model, the idea that the agent has of its world, are false in this case. The child has to first understand that sometimes it's easier if you do a task fast, and then learn it. So before you really understand the world, you can't really utilize the physics and you can't really utilize morphological computation. That's why we have the hypothesis that at first we need integrated information to understand our world, to use morphological computation, and then it goes down. So now we get to the S prime, so to the prediction. For that we have, so in order to predict that next point in time internally, the agent has this node S prime t plus 1. And we want to, the agent wants to have this internal world model, so S prime t plus 1, depending on the controller of the actuator, to be as close as possible to its empirical world model, so to the things that it actually experiences. We optimize it by adapting the EM algorithm that we used before. So we alternate between optimizing for this world model and optimizing for the goal to not be stuck at a wall. Okay, now we can get to the results. So let's first look at the agents that are unsuccessful. So these are the ones that did not learn well. Here, you can see the success rate between 0 steps, so in the beginning this is sampled, so in the beginning it's high, and then after 20,000 steps it's really low. So these ones are the ones that are not successful. In the middle we have the integrated information, and on the right we have the two-dimensional views of the results for the integrated information. So on the top, divided to that sensor length, and here after the steps. So on the top we see that we still have this decline. This is the one that I showed you before. And on the bottom we see that we have here just a plateau. So the integrated information goes high and stays there. Now we get to the agents that are successful. So we have a success rate of above 16%. You see on the left the success rate goes up, so they actually learn something. And then the integrated information goes down. So we have here a nice slope. And if you look at the bottom right here, we see that in the roughly first 500 steps or so, the integrated information goes up, and then it goes down. So this would be in line with our hypothesis at the beginning. But of course, if we just look at these data sets, we could come to a completely different conclusion. We could also say, okay, maybe this task is so easy that integrated information actually hinders the agent to learn. Because as long as the integrated information is high, the agents are not successful, as we see here. So in order to address that, I also train agents that are just not able to integrate information. So there, the dash connections that I showed you before are not there. So these agents learn the same way, or these agents are in the same racetrack as the others, but are not able to utilize integrated information. So just to remind you, agents that move completely random have a success rate of 7.92%. Agents with the ability to integrate information are around 15%. And the percentage of successful agents of the 500 that we trained are 35. And now we get to the ones that are not able to integrate information. And there the success rate is just above 8%. So just roughly, or just marginally above the ones that just move randomly. And the percentage of successful agents is only 2.5%. So these agents really do not learn well. Okay, this supports our intuition that learning to predict requires integrated information. The first part of the talk, so about morphological computation and integrated information, was published last year in Frontiers. And the second part should be an archive preprint that should be up right about now or maybe tomorrow, but it's submitted, it should be on the archive soon. This work is supported by the DFG within the priority program, the Active Self. Thank you for your attention.